in 4,2 helium plus ion, an excited electron is found initially at level n. When this electron falls down to n equal 2, the wavelengths of the radiation emitted is lambda equal 164.6 10 minus 9 meter. Determine n. First of all, n is greater than 2. Do I have any value in the statements where n is greater than 2? Yes, all values are greater than 2. So I cannot find the answer by thinking and elimination. So I have to do calculations. What is helium plus? Helium plus is a hydrogen-like, and the wavelengths of the transition when the electron return from higher n to lower n can be calculated by two different ways. I can say delta E equal En, where n is unknown, minus E2, and E2 is known. So delta E equal En minus E2 equal Hc over lambda, H given, C given, lambda is given 164.6 10 minus 9 meter. E2 I can calculate, E2 for hydrogen-like, E2 equal minus 13.6 Z squared divided by N squared in electron volt, or minus 2.18 10 minus 18 times Z squared divided by N squared in joule. So E2 can be calculated. So by this way I can calculate En. En equal, I apply again the formula, I can find the level n. Okay, this is method 1. We have another method, is to apply Balmer-Rydberg formula. 1 over lambda equal RH times Z squared for hydrogen-like, 1 over N initial minus 1 over N final. And in this formula, Ni is lower than Nf. What is Ni? The electron is found initially at level 2, and N final, we have to correct, this is N final, and N final is the higher energy level. So by this way, I can calculate N final 1 over lambda in centimeter. Why lambda in centimeter? Because RH, the Rydberg constant in this exercise, 109,677, is given in centimeter minus 1. So by this way, I can find N final, we correct it, N final equal 2.99, so N final equal 3. Pay attention, in this formula, lambda and RH should be in the same unit. If RH in meter minus 1, so lambda in meter, RH in centimeter minus 1, so lambda should be in centimeter. So the correct answer is A. Exercise 14. A hydrogen atom is in its ground state. Hydrogen atom, that means a system of one electron. And this electron is at the ground state, so this electron is initially at level 1. Absorb a photon of frequency 3.223 times 10 to the power 15 second minus 1. So it absorbs energy of frequencies 3.223 times 10 to the power 15 second minus 1. So this electron at level 1 will pass to higher level N. Following this process, the electron should return from N higher to N lower. But it's not necessary that this electron return to the N equal 1. So the question what is the final energetic level of the electron of this atom. I draw the sequence of absorption and emission. Initially, the electron is at the ground state. It absorbs energy of frequency 3.223 10 15 second minus 1. It will pass to level N1. The atom becomes unstable. So the electron should return to another state. By theory, it should return to n equal 1. But in this exercise, he told us that the electron returned to level N2. Okay? So N2 is between N0 and N1. And when the electron returns from N1 to N2, it will emit energy of frequency 2.98 10 14 second minus 1. So the question, what is N2? By the same way, we can apply the Balmer-Rydberg formula for n initial equal 1 to n final equal N1, and by this way we calculated N1. Then we apply the Balmer-Rydberg formula from N1 to N2, but pay attention, in this case N1 is N final, N2 is N initial. So we have mu equals C over lambda, 1 over lambda equal mu over C. So 1 over lambda equal RH Z square 1 over N initial square minus 1 over N final square. And this is for hydrogen or hydrogen-like, in this case Z equal 1. So we multiply by C, C over lambda equals C times RH, Z square 1 over N initial square minus 1 over N final square. So we obtain a relation directly between mu and the energy levels. Mu1, if we apply mu1 for this relation, we consider Ni equal 1 and Nf equal N1. And then we apply this relation on the second transition, okay? But in the second transition, N1 is greater than N2. So N2 will be N initial and N1 will be N final. And pay attention that lambda and RH should be in the same international system, RH in meter minus 1. So lambda in meter and C in meter per second, or centimeter by minus 1. We have to pay attention for the use of the units. So I apply in the absorption from N1 to N2, mu1 equals C RH 1 over N0 square minus 1 over N1 square. So I calculate by this way. I put mu1 by its value, C in meter per second, RH should be in meter minus 1, and we calculated N1, which is 7. Then I apply the same relation in the emission. Emission of the photon, mu2 equals CRH 1 over. Pay attention that in the emission, N2 is less than N1, so N2 equal N initial. So 1 over N2 square minus 1 over N1 square. And pay attention for the units to use all terms in the same SI system, and we obtain N2 equal 3. So by other words, when the electron in hydrogen is at level 1, absorb mu1 equals 3.223 10 to the power 15, it passed to level 7. Then the electron return from 7 to 3 by emission of energy of frequency mu2 equal 2.98 10 to the power 14, second minus 1. So the answer is C. Exercise 15. For beryllium 3+, which is hydrogen-like, the transition energy of an electron from the second excited level to the third excited level is. We apply the energy difference. Okay, the electron return from n equal 4 to n equal 3. We calculate beryllium 3 plus is hydrogen-like, and En for hydrogen-like equal minus 13.6 Z squared divided by n squared in electron volt. The difference of energy, delta E, is always equal E final minus E initial. Delta is final minus E initial, and the final has n greater than the initial. So delta E equal E4 minus E3 equal minus 13.6 electron volt Z square 1 over n final square minus 1 over n initial square. Or you can apply delta E directly equal E4 minus E3. You find separately E4 and E3. Then you say delta E equal E4 minus E3, and you calculate the difference of energy. So delta E equal minus 13.6 times Z for beryllium is 4. So 4 square minus 1 over 4 square minus 1 over 3 square, and delta E is 10.6 electron volt. Pay attention that delta E is a positive value. Okay, so delta E, because E equal E higher minus E initial, so delta E is always positive. Can we find the answer by thinking and elimination? No, all the values are positive. So we have to do calculation in this exercise, and the correct answer is D. Exercise 16. According to Bohr model, which of the following species requires the most energy to ionize? In other words, we can say according to Bohr model, calculate the ionization energy for the following species. 7, nitrogen 6 plus, hydrogen, oxygen 7 plus, lithium 2 plus, helium plus. If we compare the species, we observe that all the species has 1 electron and several protons. In A, we have 7 protons, 1 electron. In B, 1 electron, 1 proton. In C, 8 protons, 1 electron. Okay, so this species are hydrogen-like. What is the ionization energy? The ionization energy is the energy needed, so the value should be positive, is the energy absorbed by atom to remove, by atom at the gas state, to remove 1 electron from its valence shell. So how to analyze, or what is the strategy to solve this exercise? The ionization energy, by definition, is equal E infinity minus E where the electron is found, so minus En, and E infinity is equal to 0. So the ionization energy, by definition, you can apply directly this formula. The ionization energy equal plus 13.6 Z square divided by n square in electron volt, or you can say the ionization energy equal plus 2.18 10 minus 18 Z square divided by n square in joules. So the ionization energy is inversely proportional to the place or to the energy level of the electron and directly proportional to Z square. In all the species, we have only one electron. And this electron is found at n equal 1 in the first, in the second, in the third, in the fourth, in the fifth. We have one electron. So this electron necessary at the same n, which is n equal 1. So in all the species have the same n. So the ionization energy is directly proportional to Z. We can say if n is the same for all the species with Z greater should have the greatest ionization energy. So all the ions have one electron in the same level n equal 1, which is at the ground state. According to this equation, as Z increase, ionization energy increase. So the greatest ionization energy is for the ion with the highest Z, which is the highest Z is oxygen. So the oxygen has the highest ionization energy, and the answer is C. What is the meaning the oxygen has the highest ionization energy? That means the oxygen 7 plus absorb the greatest amount of energy in order to remove one electron that is found at n equal 1. We pass to exercise 17, and this is the application of Schrödinger equation and the set of quantum numbers. Indicate which of the following combination is or are correct. We have set of quantum numbers n, l, ml, and ms, and as we know that the quantum numbers are related, n is integer number 1, 2, 3, 4, 5, 6, 7, etc. L is between 0 and n minus 1. ML is between minus L and the plus L. And MS is a plus half or minus half. So we can we eliminate the incorrect values? I pass to A. 3, 0, 0 minus half is acceptable. So A is correct. I pass to B. N equal to L equal 3. It's impossible that N is less than L. So B is incorrect. N could not be less than L. C. 3, 2, minus 1, minus half. According to this relation, C is correct, is acceptable. D. N equal to L equal 2 is incorrect. N could not be equal to L. L is between 0 and n minus 1. So D is incorrect. And the correct answers are A and C. So E is the correct answer. Exercise 18. The number of possible values for the magnetic quantum number ML that correspond to D is. What is the meaning of ML? ML describe a room, describe a box in the box representation. If I have two values of ML, so I have two rooms, and two rooms can contain maximum 4 electrons. What is the meaning of D? Sublevel D means L equal 2. So what are the values of ML possible? ML is between minus L and the plus L. So the possible values for ML are minus 2, minus 1, 0, 1, and 2. So I have 5 possible values of ml for L equal 2. 5 values of ml describe the presence of 5 rooms, and each room contains maximum 2 electrons. So the 5 values of ml describe the motion of 10 electrons. If we have this question, we can say this is the motion of 10 electrons maximum. So as a rule, you can apply it directly. For L, we have 2L plus 1 value of ml. In this case, L equal to 2 times 2, 4 plus 1. So we have 5 values. This formula can be applied directly without proof. So the correct answer is B. Exercise 19. Which of the following sets of quantum numbers describe the valence electrons of chlorine atom which has Z equal 70? First of all, we have to write the electronic configuration of Cl. Cl 17, so we have 17 electrons, 1s2, 2s2, 2p6, 3s2, 3p5. In the second part of the chapter 2, I will explain the sequence of this electronic configuration. 1s2, 2s2, 2p6, we have 10, 3s2, and 3p5, we have 5 electrons. The valence shell is level 3. And the valence electrons are the electrons on the valence shell. So the valence electrons are 3s2, 3p5, we have 7 electrons valence. So the valence electrons are 3s2, 3p5. These valence electrons are found on n equal 3. So we can eliminate A, we can eliminate E, because in A n equal 2, in E n equal 4, in D n equal 2. So A, D, and E are eliminated. We have 2 possibilities, B or C. If I consider C, n equal 3, L equal 1, this is 3p, and this is 3s. N equals 3, so A, D, and E are incorrect. I can eliminate C. L equal 1, ML equal 2. ML could not be greater than L. ML is between minus L and the plus L. So C is eliminated. In this case, first of all, we eliminate A, D, and E. In the second analysis, we eliminate C. So the correct answer is B. One student can think by this way. This is the way of thinking and elimination. That means I think and I eliminate the false answers. I can find the correct one. Another student can work by other method, is to write what are the quantum numbers for 3s and 3p. For 3s2, the quantum n equal 3, s, so L equals 0. ML is between minus L and the plus L, so M equals 0, and MS equal plus half. So the first electron has quantum numbers 300 plus half. The second has 300 minus half. And we write by the same way for 3p5, n equal 3. The electrons are found on p, so L equal 1. ML is between minus L and the plus L, minus 1, minus 1, minus 1, 0 plus 1. and we have two quantum numbers. We have two spins, plus half minus half. So the possibilities for this 5 electrons, 3, 1, minus 1 plus half, 3, 1, minus 1 minus half, 3, 1, 0 plus half, 3, 1, 0 minus half, 3, 1, 1 plus half, 3, 1, 1 minus half. Then we look to the proposal and we find that B is correct. 3, 0, 0 plus half, 3, 0, 0 plus half exists in the first table. But this method takes time. So it's better to use the thinking and elimination method. Exercise 20. So the correct answer is B. Exercise 20. How many electrons can be described by the quantum numbers n equal 4, ml equal minus, ms plus half? Okay. We write for n equal 1, n equal 4, what is the possible values of L? The possible values of L are 0, 1, 2, 3. For ml, for L equals 0, ml equals 0. For L equal 1, ml equal minus 1, 0, 1. For L equal 2, the values of ml minus 2, minus 1, 0, 1, 2. And for L equal 3, the values of ml are between minus L and the plus L. So we obtain the possible set of quantum number n, L, ml. He gave us n and ml and ms. In this value, we have ml minus 2. And ml minus 2 is the room of 2 electrons, where the first has plus half. We have to correct. The second has ms minus half. Okay? We have to correct. And the second, ml minus 2, we have ms plus half and ms equal, we correct, minus half. So how many electrons can have n equal 4? L is not given. N equal 4. ml equal minus 2. We have 4 electrons. 4 electrons have n equal 4, ml minus 2. But how many electrons have n equal 4, ml minus 2 and ms equal plus 1? Are 2 electrons. In this room, we have 1 electron with ms plus half. And in the second room, we have 1 electron with ms equal plus half. So the 2 electrons have n equal 4, ml minus 2, and ms plus half. The first 4, 2, minus 2, plus half. And the second 4, 3, minus 2, plus half. So the total is 2 electrons. And the correct answer is C. Pay attention to correct ms equal minus half minus half. Exercise 21. How many electrons in atom can have the quantum numbers n equal 3, L equal 1? What is the meaning of n equal 3 and L equal 1? This is the orbital 3p. How many electrons can we have in 3p? 3p is 3 rooms. And each room contains 2 electrons. So 3p is the motion of 6 electron maximum. So the correct answer is C. 3p describes the probability of presence of 6 electron maximum. The correct answer is C. Exercise 22. How many electrons can be described by the quantum numbers n equal 3, L equal 3, ml minus 1? First, n equals 3, the possible values of L are 0, 1, 2. In our example, n equal L. This is impossible. So this description of quantum numbers is incorrect. L could not be equal to 3 in this case. So there is no any electron having L equal to 3. And the answer, we have 0 electron. So the correct answer is A. Exercise 23. Which of the following is incorrect value for the magnetic quantum number ml of an electron in 5D? 5D means n equal 5, and since we are talking about d subshell, so L equal 2. The possible values of ml are between minus L and plus L. So ml equal minus 2, minus 1, 0, 1, and 2. B is acceptable, C is acceptable, D and E are acceptable. So the incorrect answer is A. The incorrect value is in A, so the correct answer in this exercise is A. #24. Which gas phase atom in its ground state could have electron with the quantum numbers 3, 2, 0, minus F? And we have several possibilities: sodium, magnesium, phosphorus, and titanium. First of all, I have to write the electronic configuration. Sodium 11 electrons, 1s2, 2s2, 2p6, 3s1. Magnesium 12 electrons, 1s2, 2s2, 2p6, 3s2. Phosphorus 15 electrons, 1s2, 2s2, 2p6, 2p6, 3s2, 3p3. This is error in typing. Okay, so 1s2, 2s2, 2p6, 3s2, 3p3. And titanium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. I will explain later the sequence of the electronic configuration. So for n equal 3, L equal 2, this is the notation of 3d orbital. In sodium and A, we don't have 3d. In magnesium and phosphorus, in the electronic configurations, we don't have 3d. So n equal 3 and L equal 2, that is the notation of 3d orbital, exists only in titanium, where we have 3d. So the correct, only titanium could have this electronic configuration, and the correct answer is D. Exercise 25. The maximum number of electrons having the quantum numbers n equal and ms equal plus half is. We have several possibilities. Okay, I have to write the maximum number of electrons. This is a rule that can be applied directly. The maximum number of electrons in a shell. That means for a certain value of n, we have maximum 2n squared electrons. That means in level 1, 2 times 1 square, we have maximum 2 electrons. In level 2, we have 2 times 2 square, 2 square 4, we have maximum 8. In level 3, 2 times 3 square, we have 18. N given in this case is N equal 4. 4 square 16 times 2 equal 32 electrons. That means in the level N equal 4, we have maximum 32 electrons. These 2 electrons could not have the same spin. These 2 electrons are distributed in 16 rooms. And in each room, we have 2 electrons. One of these electrons have ms plus half, and the second electron has ms minus half. So in this 32 electrons, we have half of these electrons with ms plus half, and the second half have ms minus half. So in this 32 electrons, we have 16 electrons having positive spin plus half. And the correct answer in this case is A.